Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics series, where I am trying to help you to achieve your dream of getting 60 in upcoming KCET 2025 exam. So in that journey today I am going to discuss about thermal properties of matter. We have already completed all the chapters of second PU and almost all the chapters of first PU are also done. Only few chapters are left. So today we are going to discuss thermal properties of matter, complete chapter as well as chapter PYQs. But before going into the chapter, I request you to join our WhatsApp channel, because there everything is happening in through our WhatsApp channel. Every Sunday there is a KPL test. You know that we will be giving you a question paper in the morning, and you can download the question paper from the WhatsApp channel, solve it, and at night I will be there with the solution. So that was the process. I hope you are familiar with that, and if you are new to the channel, don't forget to subscribe to our channel so that you get all the latest update related to KCET 2025 exam. And now let's start with the list of content that we are going to discuss today. First we will start with the basic concept of temperature. Next we will discuss ideal gas equation, then we will discuss thermal expansion, and then we will discuss about specific heat, calorimetry, etc. Then we will discuss about calorimetry obviously, then we will discuss heat transfer, then we will discuss black body radiation briefly, and then obviously the PYQs from this chapter. Now based on the trends of the PYQs, most of the PYQs are based on either specific heat or calorimetry nowadays, but there are certain year where question came from black body radiation, namely the Newton's law of cooling. Okay, so those are also came, and Newton's law of cooling is very important if you are preparing for JEE exam or NEET exam. So this is a semi important, not super important, not medium important. It's a less important chapter. Okay, every year about one question comes from this chapter. So without any delay, let's discuss with the first topic of today, that is temperature. So what is temperature? So heat is the form of energy transferred between two systems or systems and its surroundings by virtue of temperature difference. So what is heat? Heat is basically a form of energy. Okay, heat is a form of energy which can transfer from one object to another. In the other words, it can be called as energy in transfer. Okay, so heat is a form of energy that can transfer from one object to another. Okay, and when the heat transfer happens, when there is a temperature difference. So if we have two objects, say A and B, okay, and there is a temperature difference, then if you connect them, there will be a heat transfer. Okay, if the heat is not getting transferred, that means both of them have the same temperature. Okay, so that was the basics of zeroth law of thermodynamics, if you remember. Right, now we are not going into that. Now there is a relationship between degree Fahrenheit and degree centigrade. What is that? That is F minus 32 by 180 equals to C by 100. Now, so here F is the Fahrenheit and 32 is the difference between upper fixed point and lower fixed point. Okay, so 32 is the lower fixed point. My mistake. 32 is the lower fixed point, and 180 is the difference between upper fixed point and lower fixed point. Okay, so Fahrenheit scale is lower fixed point is the temperature of freezing of ice, which is 32 degree Fahrenheit. Okay, and upper fixed point when is the boiling point of water, which is 212 degree Fahrenheit, right? And Celsius is easy. Okay, it starts with 0 is our freezing point of water, and 100 degrees is the boiling point of water. So basically C minus 0 by 100 minus 0, so basically it is C by 100. Okay, so you can remember that, or you can remember F minus 32 divided by 9 is equal to C by 5. That is also fine, but this is easier to remember, that's why I have given you like this. Now let's discuss about ideal gas equation briefly. Okay, ideal gas equation, we know that PV equals to nRT. Now I have not seen any direct question coming from ideal gas equation, but in the next chapter, thermodynamics chapter, okay, this is very important because you have to apply this equation to solve certain questions, so that's why it becomes important. Okay, otherwise no direct question. Okay, pressure is 1 atmosphere, volume is 2 milliliter, what is the temperature, like that the questions never came, right? But this equation is important, and based on this equation some other questions, maybe some interrelated questions you may need to solve. That's why I gave you this formula, and this another formula, P1 V1 by T1 equals to P2 V2 by T2, and this is equals to constant, obviously, right? So this one, these two we already know pretty well. Now let's move on to the next part, thermal expansion. What is thermal expansion? Let's see. Coefficient of volume expansion. Linear expansion is not important. Okay, volume expansion is when you heat one object, okay, heat one object and its volume increases after heating it, or if you cool it down, its volume shrinks, right? So that is called volume expansion. It can be for any object, okay, and the definition of volume expansion is given by 1 by V dV by dt. So how much volume changes when you change the temperature by some amount and you divide it by the original volume, you get it, the coefficient of volume expansion. It is this law is general. This is for solid, liquid, gas. It is valid for everything. Okay, but for ideal gas, and if you draw the graph of alpha versus T looks like this. Okay, sometimes they have a tendency to ask questions based on the graph. So graph is, you have to remember this graph. This is slightly important, and if you apply the law of PV is equal to nRT in this equation, then you get that alpha V is basically 1 by T. Okay, alpha V is 1 by T. So if you plot the graph of alpha V versus 1 by T, you will get a straight line graph. Okay, obviously the graph is not, even though if you backtrace it, it should end at 0, but 0 means absolute 0 temperature. So that's why, or infinite temperature, actually 1 by T, 0 means infinite temperature. So that's why they have not drawn it to till this value, otherwise it is linked to this point. Okay. Now, so this is the graph, and this diagram is taken from one of your previous year question paper. So they asked you what is the relationship between alpha V and temperature for an ideal gas. So if you know this relationship, you know that alpha V is directly proportional to 1 by T, so it will be a straight line graph, right? So it will be a straight line graph like this. It is not a curve, so you can answer this question. Now let's look into thermal expansion, anomalous expansion of water. Okay, anomalous expansion of water means what? We know that water does not heat up like normal material, but it has a peculiar tendency. What is that? That when you increase its temperature, okay, its volume, if you start from, obviously water starts at 0 degrees Celsius, right? So 0 degree, at 0 degree it starts melting and it becomes water, right? So at 0 degrees Celsius, what happens is that the volume is not the smallest volume. Okay, so its volume initially start to decrease. Okay, so volume, instead of increasing, as you are increasing the temperature, instead of decreasing in the volume, increasing in the volume of water decrease initially. Up to how much? Up to 4 degrees Celsius. Up to 4 degrees Celsius, its volume decreases. Okay, so this is a very important point for water. Up to 4 degrees Celsius, the volume of water decreases. After 4 degrees Celsius, it behaves like normal objects and its volume increases. Okay, so if you plot this graph from here, this is the normal behavior of all the material. Okay, this is the normal behavior for all the material. As you increasing the temperature, volume increases, right? But till this point, okay, up to 0 to 4, something peculiar is happening. Instead of increasing in volume, okay, its volume decreases. That's why it is called anomalous expansion of water. So which is an anomaly, which is not common. Okay, anomaly means something something which is not common. Okay, so that's why it is called anomalous expansion of water. In terms of density, the density of water increases as you increase the temperature from 0 till 4 degrees Celsius. At 4 degrees Celsius, the density of water is maximum. Okay, at 4 degrees Celsius, the density of water is maximum. Okay, so it is basically 1 gram per cc, or you can say 1 kg per meter cube times 10 to the power of 3, whatever you are interested in. Okay, basically we will say 1 gram per cc. So basically when we say 1 gram per cc is the density of water, we generally assume it constant throughout the temperature. Actually it is not. It is at 4 degrees Celsius only. Okay, as you go down and up, it changes slightly. Okay, as you can see, it is decreasing. Initially it is increases till 4 degrees Celsius, it becomes maximum, then it decreases as you are increasing the temperature. Okay, as you increase the temperature, its density slowly decrease, right? So this is a very interesting concept, and based on this concept there are few questions that came in KCET. We will look into that while we are doing the PYQs from this chapter. I'm not going to discuss the questions right now because all the PYQs are there at together, so that if you want you can go and check them from the video. Okay, now let us look into the specific heat. So what is specific heat? The change in the temperature of a substance when a given quantity of heat is absorbed or rejected by it. So basically the change in temperature when you give some amount of heat energy. Okay, what will happen if you supply something with external heat energy? Okay, so for example, you have a container full of water. You place it on top of a gas stove. Okay, so what will happen? The water will slowly start absorbing the heat from the stove, right? So as it's absorbing the heat from the stove, it will slowly increase in its temperature. Now how fast or how slow it will increase the temperature, that depends on this term called specific heat. Okay, so the change in temperature of a substance when a given quantity of heat is absorbed or rejected, that is called specific heat. Okay, specific heat capacity is, if you make the mass unity, unity means 1 gram or 1 kilogram. Okay, where it is, if you are using SI unit, okay, if you make it 1 kilogram, then whatever amount of heat it requires to increase its temperature to 1 degree Celsius, that is called specific heat capacity. So if you make the mass 1, if you change the increase in temperature to 1 degree, that is called specific heat capacity. Okay, if you supply if you supply H amount of heat to an object, okay, if you supply H amount of heat to an object and its mass is M, its specific heat capacity is S, then its change in temperature or increase in temperature is delta T, then the relationship between H and delta T is given by H equals to MS delta T. Clear? So delta T is the difference in temperature, very important. Okay, so heat rejected by or by absorbed, this is the amount of heat rejected or by absorbed, and this is the heat capacity. Okay, now there is one more type of heat which is called latent heat. Specific heat is applicable when the object is not changing its state. Okay, so if you are heating a liquid, that liquid is still at liquid phase. So I gave you the example where you are trying to boil a water. So as long as the water is still water, you can apply this formula. Okay, but when it starts to change, when it is boiling, okay, it starts to change its phase. Okay, if you keep it on the stove, what will happen? It will, after some time, it will keep on boiling unless all the water is vaporized, right? So that process, when the water is getting converted from water to vapor, you cannot apply this thing, because at that point of time the heat required by it is very fixed. It does not depend on temperature, because delta T is 0. We know that during phase change no temperature change happens, right? So we know that water boils at 100 degrees Celsius. So that, what is the meaning of that? That when you take the water to 100 degrees Celsius, the 100 degrees Celsius water converts into 100 degrees Celsius water vapor, right? So temperature is fixed at this state. So you cannot apply this formula. So for that, what amount of heat is required is given by something called latent heat. Okay, latent heat can be classified into two more parts. Okay, we will see that. So the heat required during a change of state depends upon the heat of transformation and the mass of the substance undergoing the change of state. So obviously it depends on the mass and heat of transformation. So this heat of transformation is called latent heat. Okay, so when how many phase change can happen in our day-to-day life? We have seen that ice can melt from ice to water. Okay, so from solid to liquid. Okay, now if you keep on heating it, water will be converted into from water to vapor. So that means liquid to gas. Right, so there are three phases. We know solid, liquid, gas. There are other phases. Plasma is one state, but we are not going to discuss about those phase changes. Those are complicated things. Okay, so normally only solid, liquid, and gas. Okay, so solid, from a solid to liquid, there is a phase change. Latent heat is required. Okay, from liquid to gas, there is a phase change. Another latent heat is required. Okay, now the latent heat for melting is called latent heat of freezing. Sometimes latent heat of freezing or latent heat of melting, but latent heat of melting we do not use. We use latent heat of freezing, and when it becomes vapor, we say latent heat of vaporization. Okay, why it is freezing? Because there are two things. If you give that much amount of heat, then it will melt. Similarly, if you take out that much amount of heat, it will be freezing, right? So this is the exact amount of heat that is required to melt certain object or freeze that object. Similarly, in case of vaporization, if you apply that amount of heat, it will either be converted into vapor, or if you take out that amount of heat, the vapor will be converted into liquid, condensed into liquid. Okay, so this is the very important thing. Also, when you keep two objects of different temperature, we already know that suppose this temperature is T1, this temperature is T2, and if you keep them together, okay, through some medium or direct connection, what will happen? They will exchange heat. Okay, suppose T1 is greater than T2. Okay, then what will happen? T1 will gain extra amount of heat, so heat will flow from T1 to T2, right? T1 is greater, so T2 will gain the heat. Okay, not T1. So he will gain some amount of heat. So now we can see that this object will lose some heat and this object will gain some heat. Okay, now energy, from the conservation of energy principle, we can say that amount of heat lost by this object is equal to amount of heat gained by this object. Okay, it is not 100% correct because there will be some heat leaked into the atmosphere, but if you do it carefully using certain instrument called calorimeter, then you can reduce this loss of heat to almost 0.1%. So almost every heat is getting transferred from object to the second object, right? So this is the principle of calorimetry, where it is said that the heat lost by an object is heat gained by another object. So there is a saying in our common day-to-day life: if the loss of someone is gain of another person, right? So if you losing something, that means someone else is gaining from that. Okay, so here the same thing is applicable in heat as well. If some object is losing heat, another object is gaining heat. Okay, clear? Now let's move on to the problem. So there is a basic problem based on the principle of calorimetry. Everything that we have done in the previous slide, that will be discussed in this problem, and this problem is from KCET 2024. The problem is big, it looks difficult, but if you follow step-by-step process, this is a very easy question. Okay, that's why I say that this chapter is relatively easier, so you have to study this chapter so that you can answer that one question coming from this chapter. What is the question? A solid cube of mass m at a temperature of theta naught is heated at a constant rate. Okay, it becomes liquid at a temperature theta 1. Okay, so basically suppose you have a piece of ice say at minus 15 degrees Celsius. Okay, you started heating it, then at 0 degrees Celsius it starts melting, right? So it becomes liquid at a temperature theta 1 and vapor at temperature theta 2. Okay, so it becomes liquid at what temperature? At theta 1. It becomes vapor at what temperature? At theta 2. Okay, let S1 and S2 be the specific heats in its solid and liquid states. This is the solid one when it is in ice phase, and this is liquid one when it is in water phase, right? So this is the specific heats that are given respectively. If LF and LV are latent heat of fusion or freezing is same. Okay, latent heat of fusion and vaporization respectively, then the minimum heat energy supplied to the cube until it vaporizes. So what are the states? First let us write it down. So you have to break this problem down to individual parts. Okay, if you break it down, this is a very easy simple problem. So you have a solid. First state is solid. Okay, and what is the temperature? Temperature was theta naught. Okay, now you heat this solid until it becomes liquid. Now before getting into liquid, it has to become a solid of temperature theta 1, right? Only if it reaches that point, then only it will be able to melt, right? So if you are heating an ice cube, you started at minus 15 degrees Celsius, but the ice will remain ice till it reaches 0 degrees Celsius. At 0 degrees Celsius, the ice will start melting. So it will remain solid till it reaches its melting point, that is theta 1. Now at theta 1, the solid will be converted into liquid, right? Clear? Tell me if I am making any mistakes in this. Now it will be again liquid at temperature theta 1. Now it will be again heated till it reaches vaporization, till it reaches vapor, right? Till it becomes vapor. But before becoming into vapor, it will be a temperature of the boiling point theta 2, but it will be still a liquid. After it becomes liquid of theta 2, it will start boiling and it will become a vapor. Okay, so they asked you what is the total amount of heat required for it to reach from solid at theta naught to vapor at theta 2. That is the question. Okay, so what we will do, we will calculate the entire heat required for each of the steps. So how much heat required in this step? We know that ms delta T, right? So ms1 for solid, S1 is given, and delta T is final temperature minus initial temperature, theta 1 minus theta naught. Okay, so this is the heat required for it to melt. Now what is the latent heat? Latent heat of fusion, latent heat of freezing is given by theta F. So mass is m. So how much temperature is required? MLF. ML heat required is equals to ml for melting or vaporization, right? So now how much heat is required for it, the liquid, to reach from theta 1 to theta 2? Again same formula as this, but only difference is it will be S2, and the temperature difference is final temperature is now theta 2 and initial temperature is now theta 1. Okay, only this thing will change, right? Now how much heat is required for it to vaporize? Okay, again same formula, M L V. This is the temperature required for it to vaporize. Now what is the total heat required? Total heat required is addition of all these things. Okay, so total heat required is addition of all these things. Now let's check the options. Obviously in this option 1, we see that MLF and MLV are not there, so this is not the correct option. Okay, in this case we can see that MLF and MLV are included, but not both the melting and solid state and liquid state both are not included. Only the liquid state is included. Solid state heat change is not included, so this is also not the correct answer. Okay, now let's check this one. Here we have MS1 theta 1 minus theta naught plus MLF, correct, plus MS2 theta 2 minus theta 1, yes, correct, plus MLV. So this is the correct answer. Okay, if you want to check the last option as well. MS1 theta 1 minus theta naught plus MLF, everything is same. In this case MS2 they have done theta 2 minus theta naught. This is incorrect. Okay, this is incorrect because it should be theta 1, because liquid is getting transferred from theta 1 to theta 2. So be careful, this is a trap. If you fall for this trap, then you will be incorrect. Okay, so you can answer this question if you just simply understand the concept, okay, without doing much case study. Now let's discuss about heat transfer. There are three types of heat transfer: conduction, convection and radiation, but mostly that is important from this part is conduction. Okay, only one question came in your previous last 10 years of KCET exam from this chapter, that based on conduction. Okay, what was that question? That was based on how it will who will conduct heat faster. Now you have to realize that if area is more, okay, if area is more, heat transfer will be faster. This is the amount of heat transferred from through an object. Suppose we have a rod. Okay, let's explain this equation. What is the meaning of this equation? Okay, the equation means that suppose we have a rod, okay, and you are transferring some amount of heat through this rod. Okay, how much amount of heat will be transferred is based on this formula. Okay, so suppose this end is at higher temperature Tc, this end is at lower temperature Td. Then how the amount of heat will be transferred is based on this. So this is the amount of heat is getting transferred. So K is a conductivity of the material. It depends on the property of material. A is the area of cross section. A is the area of cross section. Higher the area, faster or more amount of heat will be transferred, and longer the length, okay, smaller will be the heat produced. Okay, so heat transferred is basically proportional to the area, and heat transferred is inversely proportional to the length. Okay, this one you have to remember. Okay, now let's move on to the next part, black body radiation. Now in the black body radiation we have Stephen-Boltzmann law. Okay, Stephen-Boltzmann law says that heat is basically this is emissivity, how much heat is being emitted by a black body. Okay, how much heat is being absorbed by a black body. Emissivity and absorptivity are, there is a relation, but mostly we are interested in how much heat is being radiated. So E is the emissivity, sigma is a constant, Stephen-Boltzmann constant, A is the area, okay, of the black body, T is the temperature of the black body, and Ts is the temperature of the surrounding. Okay, so this is the very important formula. You can remember that H is basically EA epsilon T to the power 4 minus Ts to the power 4. This, based on this formula, no question so far has come, but maybe in future some questions, very easy questions may come from this formula. So you need to remember that heat radiated is based on, dependent on the temperature to the power 4. Okay, if the atmosphere around this is absolute 0, then you can make Ts to the power 0, and you can take this as only T to the power 4. Okay, now Newton's law of cooling is very important. Based on this, 2 questions or 3 questions I think came in your previous KCET exam. So this is very important. So what is that? d theta by dt equals to k delta t. So they all have different meaning. What is the meaning of d theta by dt? d theta by dt is the rate of changing of temperature. Okay, suppose I have an object which is at 60 degrees Celsius and it changes, it goes to 50 degrees Celsius, say in 10 minutes. Okay, so the rate of change of temperature is called d theta by dt. Okay, so how much temperature changes? Temperature changes by 10 degrees, right? 60 minus 50, okay, is 10 degrees. And how much time was taken? Time was taken is 1 minute. So we can say that degree and minute. So rate of change of temperature is 1 degree per minute. Okay, 1 degree per minute. So this is the d theta by dt. You have to be careful, there is another delta t here. What is this delta t? This delta t actually represents what is the temperature difference between the average of these two and room temperature. Suppose the room temperature of that day was 25 degrees Celsius. Okay, so room temperature was 25 degrees Celsius. Then what is delta t? So first what you have to do, you have to find the average of 60 and 50. Average, how to calculate average? Just add them and divide them by 2. So adding them is 110 divided by 2 is 55. Okay, so what is delta t? Delta t is 55 minus room temperature, that is 25, that is 30 degree. Okay, and this is a constant. This k is a constant. If you know all the values, you can calculate the value of k as well. So k is basically k times 31 equals to k times 30. Right? So k is basically not degree, it will be per minute. K will be 1 by 30 per minute. Degree will cancel. Okay, so k is a constant. Okay, and it determines how fast an object cools down. Okay, so if the temperature, starting temperature is very high, then that object actually cools down faster compared to which object has a lesser temperature. Okay, so that's why hot object cools down faster compared to a middle, somewhat at close to the room temperature, right? So as the temperature decreases, thus rate of cooling down slows down, right? So this is very important that you have to remember. As the temperature decreases, the rate of cooling down decreases. Okay, so it becomes it takes longer time to cool down. Okay, so basically this relates the rate of cooling down. Okay, we'll see some numericals from that in our PYQ section. So let's start with one PYQ, and as I said, most of the recent PYQs are based on the calorimetric principle. We solved one question from 2024. Let's look into 2023 problem. Okay, 100 grams of ice at 0 degrees Celsius is mixed with 100 grams of water, okay, at 100 degrees Celsius. Okay, so 100 grams of ice at 0 degrees Celsius and 100 grams of water. This is not vapor. Okay, this is at water at 100 degrees Celsius. The final temperature of the mixture is, what is the final temperature of the mixture? Take LF equals to 3.36 times 10 to the power of 5 joule per kg, and specific heat of water is 4.2 times 10 to the power of 3 joule per kg per Kelvin. Okay, so let's start. How to start this problem? First of all, the mass of ice is 100 degrees Celsius. Okay, so and mass of water is 100 grams. Okay, so both of them needs to be converted into kilograms because all the constants are given in terms of kilogram. What is 100 gram? 100 grams is equals to 0.1 kilogram. Right? You divide it by 1000, you will get 0.1 kilogram. This much is clear. Now what is happening in this case? Let's understand that. So 100 grams of ice, 100 grams of ice, initially what it will do, it will convert into 100 grams of water. Okay, then it will reach to some temperature, say theta. Okay, so this is the step for the ice. This is for ice. This is ice. Okay, this is water. It started at 0 degrees Celsius, it ended at theta degrees Celsius. Okay, now for the water, hot water, okay, let me write the kg value so that don't get confused. 0.1 kg, 0.1 kg, and for water also it was 1.1 kg. It started at 100 degrees Celsius, and after the entire process is over, it again reaches the same temperature theta. The final temperature should be same for both the cases, right? Now in this case you can see that this is absorbing the heat and this is radiating the heat or giving away the heat, and from the principle of calorimetry, if we can calculate these two heats, we can say this is exactly equals to this amount of heat. Okay, so now let's start with the process. So how much heat is required to convert this 0.1 kg ice into 0.1 kg water? Okay, so how much heat is required for melting? So here I am saying melting. How much heat is required for melting? To melt, we know that we calculate them by the mass times the latent heat of melting. Okay, latent heat of fusion, latent heat of melting, right? So this is MLF. M is 0.1 kilogram and LF is given here 3.36 times 10 to the power of 5. We have already taken care of kilograms because it is in kilograms, so we can say this is in joules. Unit is not important because as obviously we are just doing the values only. So 3.36 times 10 to the power of 4. Okay, 0.1 10 to the power of 5, so it will be reduced by 1, so it will be 10 to the power of 4 joules, right? So melting of ice, we have calculated how much heat is required. Now how much heat is required for it to reach start at 0.1 kg of water to reach theta degrees Celsius. Okay, now its temperature is again 0 degrees Celsius. So 0 to theta, its temperature is increasing. So how much heat is required for increasing? How much heat is required? We know that it is ms delta T, right? ms delta T. M is 0.1. S is given here 4.2 times 10 to the power 3. And what is delta T? Delta T is the temperature difference. So initial temperature is 0, final temperature is theta. In this case theta is more, so theta minus 0. Right, theta is the final temperature which is more than 0, so we have written it like that, or theta minus 0 is what? Theta only. So this is the total heat that is being given out by this ice. Now taken by this ice. Now how much heat is given out by this water? This is simple. For water it is simple. Water started at 100 degrees Celsius and it end up at theta degrees Celsius. So theta is less in this case, 100 is more in this case. How much heat is required for that? Heat for decreasing temperature. Here it is decreasing. How much it is required for that? We know that ms delta theta, ms delta T. So what is m? M again 0.1. Both ice and water are of the same mass. What is s? S will be same for water. And what is delta T? In this case 100 is more and theta is less. So it will be 100 minus theta. Okay, so this is the exact formula. So let me simplify this a little bit so that you can have a good value here. 4.2 times 10 to the power of 0.1, 10 to the power of 3, 10 to the power of 2 theta. Okay, so this is the increasing value. What is the decreasing value? We have to divide it and again calculate it, but what we will do initially, at least we reduce this part. Okay, so what we will do is 0.1 and 10 to the power of 3, they will cancel each other by 10 to the power of 2, so we can write this 10 to the power of 2, 100 minus theta. Now from the calorimetric calculation we can say that H decreasing should be equals to H melting plus H increasing. Okay, so this much heat was absorbed by the ice and this much heat is given out by the water. So they should be equal, right? So we have written like that. Now if I break this bracket so that it will be helpful for us to calculate, 4.2 times 10 to the power of 2 times 100 minus 4.2 times 10 to the power of 2 times theta. Okay, so let me write this again, or 4.2 times 10 to the power of 2 times 100. So we can write this as 10 to the power of 4, right, minus this one, 4.2 times 10 to the power of 2 theta equals to, what is HM? HM is 3.3 times 10 to the power of 4. Okay, 3.36, 3.3. Okay, I am just taking 3.3. We will calculate the exact value later on. Okay, and then HI. What is HI? HI is 4.2 into 10, the same value, but in a opposite sign. So 4.2 times 10 to the power of 2 theta. Okay, so what we will do? We will take this on the other side. So it will become 4.2 minus 3.3 to the power 10 to the power of 4. So 10 to the power 4 is common in both the cases. So we have taken this on our left hand side and did the negative sign because it was positive in this side. So once it comes to that side, it becomes negative. And we have taken all the theta related term to the other side. So this one was negative in this side. So if you take this on the other side, it will become positive. So 4.2 times 10 square plus 4.2 times 10 square whole times theta, right? Theta we have taken common. Now if you see that both of them are equal, so what is the value of x plus x? 2x, right? So instead of adding them, what we will do, we will simply multiply them by 2. So we will get 8.4 times 10 to the power of 2 theta, right? So 2.4 times 4.2 times 2, right? Clear? Now I have to erase one of them. Let me erase this one, this side. What is the value of theta here? So theta will be equals to 4.2 minus 3.3. What is the value? 0.9, right? 0.9 times 10 to the power of 4 divided by 8.4 times 10 to the power of 2, right? Now let me borrow one of the 10 from this. So we will get that 9 times 10 to the power of 3. We have taken 10 from this 10 to the power 4. It is a bank. It has 4 zeros. Out of those 4 zeros, I have taken 1 zero and multiplied with 0.9. So it becomes 9, right? Divided by 8.4 times 10 to the power of 2. Now this is almost equal because we have reduced 3.36 to 3. So it will be cancelled and we will get this will as 10. So 10 degrees Celsius is the answer. This is a long question. Okay, the process requires a time to solve this question. So if you get this kind of questions, don't try to solve it immediately. Solve it at the last moment. Okay, when you have solved all the questions. So if you, but this is a very straightforward step-by-step process. So there is a very little chance of making mistakes if you are doing the step-by-step process correctly. So, but if you want to answer these questions, first try to answer all other questions. At the last time you can answer this question and find the answer. Okay, now let's move on to the next question. This is a direct straightforward question. Okay, I already explained the answer for this question. What is that? Which of the following curves represent the variation of coefficient of volume expansion of an ideal gas at constant pressure? So we know that coefficient of volume expansion for ideal gas is proportional to 1 by temperature. So it will be a straight line when you plot alpha v versus 1 by T. Okay, this is the correct answer, not this one. Okay, be careful. What is the proportionality relation? If it is proportional to temperature, then the graph would have been like this. If it is inversely proportional, then it will be 1 by T. Okay, or if it is, they might confuse you. This is alpha v. Next time they ask the question, they will not give you this graph. They will give you something like this. Okay, so this will be the graph if they give you alpha v versus T graph. Okay, inverse proportional graph, we know that inverse proportionality graph, it looks like this. Okay, so this will be like this, right? Now next question. A sphere, a cube and a thin circular plate, all same material and same mass, initially heated to the same high temperature, are allowed to cool down under similar condition. Then plate will cool down fastest and sphere will be the slowest. Cube will cool down the fastest and plate will be the slowest. Plate will cool down the fastest and cube will be the slowest. Sphere will cool down the fastest and cube will be the slowest. Now, out of all these objects, which of them has a higher surface area? Okay, surface area wise, the plate will be very thin and it is very large. So it will have a larger surface area, whereas sphere will be very compact and it will have the smaller surface area. Higher the surface area, the rate of cool down is higher, right? So we have learned that heat transfer is directly proportional to area. So higher the area will be faster will be the rate of cool down. Okay, so plate will cool down fastest and sphere will be the slowest. So correct answer is option A. Right? Now next question. A cup of tea cools down from 65.5 degrees Celsius to 62.5 degrees Celsius in 1 minute in room temperature at 22.5 degrees Celsius. Okay, how long it will take to cool down from 46.5 degrees Celsius to 40.5 degrees Celsius in the same room? Now this question is based on Newton's law of cooling. Okay, so this is a little long question, this is little elaborate question, but it is a very straightforward question. What is Newton's law of cooling? If you remember, d theta by dt equals to k delta T. Okay, so for the first case, for the case 1, it is given, everything is given. A cup of tea cools down from 65 degrees Celsius to 62 degrees Celsius at room temperature 22.5 degrees Celsius. Okay, so this is the first case. So first case, what is delta theta, d theta by dt? So in this case, d theta is the change in temperature from 65.5 to 62.5. 65.5 minus 62.5, that is equals to 3 degrees. Okay, now what is dt here? Dt is given 1 minute. No need to convert it into seconds right now, we will keep it at 1 minute. Now what is delta T? K we don't know. K we have to find from the given information in 1. What is delta T in this case? That is important. To find delta T, what we have to do? First we have to find the average of these two temperatures. Okay, what is the average temperature? So theta average, we have to simply add them now. 65.5 plus 62.5 divided by 2. Okay, so 60, 120 plus 128. 67, 128 divided by 2. So the average is 64 degrees Celsius. So average is 64 degrees Celsius, then what is the temperature difference? Delta T. So delta T is nothing but final average temperature minus room temperature. Okay, this here you have to be careful, slightly careful while you are calculating this temperature. Okay, so it will be 1.5 and 41.5 degrees Celsius. Okay, so this is the temperature difference. Now we apply the Newton's cooling law. So 3 by 1 equals to, my mistake, k times 41.5. Okay, so you can get k is basically 3 divided by 41.5. We have calculated k from the given equation. So be careful while calculating this. You have to do again step by step process. Newton's law of cooling, if you are preparing for JEE mains exam or NEET exam, you have to be very profound with this formula. At least one question comes from based on this Newton's laws of cooling very often. So you cannot ignore this if you are anyway preparing for JEE mains. But for KCET, okay, it is optional questions. If you see that okay it is too difficult, you can skip that question anytime, right? But if you are preparing for getting 60 out of 60, you cannot skip. You have to learn everything. Okay, and if you are thinking okay if I get around 50 55, fine, I can skip this, no need. Okay, now again we are going to apply the same process for the next part as well. So in this case, in the part 2, let me clean here and do this in this here, okay, so that you can see everything. So for part 2, what is happening is what is delta theta, d theta, sorry, what is d theta? So it is changing from 46.5 minus 40.5. so now it is changing 6 degrees Celsius. Okay, now the change in temperature is 6 degrees Celsius. Now what is the dt? dt we don't know, we are trying to calculate dt in this case, but what we know, we have to calculate delta t. So how to calculate delta t? First you have to calculate the theta average. What is theta average in this case? 46.5 plus 40.5 divided by 2. Now this is a trap in this kind of questions. Okay, you might think okay for the temperature change 3 degrees 1 minute is taken. Here the temperature change is 6 degrees, so 2 minutes will be taken. So that will be wrong, because not only it depends on the change in temperature, it also depends on the difference in temperature. That is why Newton's law of cooling problems are little bit tricky. Okay, so it will be 47 plus 40, that is 87 by 2. Okay, 40 40 80 87. So 87 by 2 means 43.5 is the average temperature, right? So if this is the average temperature, then what is delta T? Delta T is 43.5 minus the room temperature 22.5. So the difference is 21. Okay, so this is the theta, this is the delta T. Now apply the law of cooling. So d theta by dt is equal to k delta T. So d theta is 6 here, dt we don't know, k is already calculated, 3 divided by 41.5. Okay, and delta T is 21. Okay, so dt will be 6. So let's do the cross multiplication. This will multiply here, everything else will come to this side. So 6 is already there as a numerator, this 3 will come to the denominator, this 3 will come down to the denominator, and this will go up. So 41.5, and this was in numerator, so this will go down again in this case, divided by 21. Okay, now this is easy to calculate. This is 2. Now how to calculate this one? Our best friend, approximation method. 21 and 41.5. So we can approximate to be 2, right? 21 times 2 is 42. So almost 42 is here. So we can approximate to be 2. So it will be 2 to the 4. Okay, so it will take almost 4 minutes. Okay, so correct answer is 4 minutes. So if you just assume that 2 minutes will be the answer, then you are very wrong. After solving you realize this is not 2 minutes, it is going to be 4 minutes. So do not guess such questions. Even if you guess, it will be 90% of cases it will be wrong unless and until you are doing the correct guess. Okay, now let's move on to the next question. Again this question again 2016 also based on Newton's law of cooling. Okay, a pan filled with the hot food cools from 94 to 86 in 2 minutes. Okay, so I am not going to explain too much because everything is given here. D theta, this is the case 1. So what is the pattern for Newton's law of cooling? First they will give you one part where everything is given. Okay, and for the second part they will either ask you to find the time, or they will ask you after some time what will be the temperature. Okay, so this is the basic pattern of Newton's law of cooling, and most cases they will give you after how much time only. Okay, so first part we will calculate K. From the given information we will calculate the constant K, and we will apply the concept of K in the second part. That is the basic thing that you have to remember. Okay, so what is the d theta in this case? D theta is 94 degree minus 86 degree, so it is 8 degrees. Okay, what is dt? Dt is given as 2 minutes. Okay, and room temperature is, when the room temperature is 20 degrees Celsius. So room temperature is 20 degrees Celsius, so theta room is 20 degrees. So first we have to calculate theta average. Theta means temperature, right? So temperature average, what is the average? 94 plus 86 divided by 2. This is how we calculate average, right? So it will be 100 plus 80, so 180 by 2. Okay, addition, no matter how you do the addition, don't use calculator. So it is 90 degrees. 90 degrees is the average. So what is delta T? Delta T is 90 minus 20, that is 70. Okay, so this is delta T. Now we will use Newton's law of cooling. D theta by dt equals to K delta T. So d theta is 8 degrees, dt is 2 minutes, K times dt is 70 degrees, right? So K is basically 4 by 70. Okay, so we have calculated K. From the first part, as I promised, first part only will be there to help you to calculate K. Now let's see the second part. What is the second part? How long it will take to cool from 74 to 66. In this problem the values are little bit good, right? So what is d theta? D theta is 74 minus 66. Okay, so as you can see, this will be again 8. Right, this will be again 8 degrees. So if you say okay, this is 2 minutes, so it will be also 2 minutes. No, the starting and ending temperature are different, so value will be definitely different. So what is theta average in this case? Theta average will be 74 plus 66 divided by 2. So 80 plus 60 is 140 by 2, that is 70 degree. 70 degree is the theta average. Now what is delta T? 70 minus 20, room temperature, average minus room temperature, so that will be 50. Okay, so let's now apply the law of cooling again. D theta by dt equals to K delta T, or let me write this like this, don't use too much head. Dt will be equals to, dt will go up, so d theta divided by K delta T. Okay, this is much easier. So d theta in this case is 8. What is K? K is 4 by 70. Okay, and what is delta T? Delta T is again 70. Okay, so it will be, wow, it is again 2 minutes. So 2 minute time will be taken. Okay, So 94 to 86 is also 2 minutes, and 74 to 66 is again 2 minutes. Okay, so this is the beauty of the problem. You don't know how long it will be taking, but I hope I have done this same thing, correct thing. Sorry, I made a mistake here. That's what I was thinking. How can it be 2 minutes? It will be 50 here. This is 50, right? Delta t is 50 in this case. So it will not be cancelling each other. They will not be cancelling each other. It will be 50. Sorry. Now I know someone was waiting that I want to comment, sir, you made a mistake in the calculation. Right? Things happen, but if you are not careful, then you make a mistake. Right? So you cannot cancel them. You cannot cancel them directly. Okay. So what will be the answer in this case? Let me erase everything and write this again. So 8 by 4. Now what will happen? This 70 will go up. So 8 times 70 divided by 4 times 50. Okay, so this 70 was in the denominator of the denominator, so it will go up into the numerator, so it will be cancelled, 0 0 cancel, 4 2s are 8, so it will be 7 2s are 14 divided by 5. Now tell me the answer. 14 by 5 without using calculator, it will be 2.8 minute. How? Multiply 2, top and bottom. 14 becomes 28, 5 becomes 10. So 28 by 10. 28 by 10 means 2.8. That's how you can do it quickly. Okay, so let me correct my mistake. It will be 2.8 minutes. Right? Now, next question. 4 rods with different radii R and length L are used to connect 2 heat reservoirs at different temperatures. Okay, which one will conduct most heat here? So we know that I told you there was a question that conduction of heat proportional to area and inversely proportional to the length. Now area is basically for a rod is pi r square, right? So what is the relation? So heat transferred will be pi r square by L. So higher the radius and smaller the L, the heat transfer will be more, right? So we have to find a combination where radius is more. So between 1 centimeter and 2 centimeter, obviously 2 centimeter is more. So 2 centimeter will conduct more heat, right? Now between L is equal to 2 meter and L is equal to 1 by 2 meter, L is equal to 1 by 2 meter is small. So in this case, the heat transfer will be more. So the combination answer is option D. Okay, so you have to find the combination for highest R, smallest L. Okay, from this given combination, given values, we see that highest R is this and smallest L is this. So this is the combination. Okay, easy question, straightforward question. Now question number 7. 1 gram of ice is mixed with 1 gram of steam. At thermal equilibrium, the temperature of the mixture is. Now this is a long question. The values are of the latent heats are not given. So you can try and solve this question. Okay, if they ask this question right now, they will give you the values. But I am giving this as a homework. Okay, you can try the previous question I solved. I think second or third question, second question of the today. So there I have solved one question, or 100 gram of water, 100 gram of ice, and 100 gram of water at 100 degrees Celsius was given. Now in this case, steam is given. So find the latent heat of steam. Okay, and then you can find what is the final temperature of the mixture. Okay, and 1 gram of ice. You can use the calorie value also. Okay, calorie, I know calorie value, many one familiar with calorie, many one are not familiar with calorie. Okay, so latent heat of fusion is 80 calorie per gram. Okay, latent heat of steam is latent heat of vaporization is 540 calorie per gram. So you can calculate that, you can find that temperature. Okay, and you can tell me the answer. Okay, Now definitely it is not 50 degree. Okay, I can tell you this is not 50 degree temperature. Okay, now water is heated from 0 degree Celsius to 10 degree Celsius, then its volume will. This question is based on anomalous expansion of water, I told you. So what happens is that its volume first decreases till 4 degree Celsius, okay, and then it increases after 4 degree Celsius. So only one option is correct, that is option B. Okay, when you heat water from 0 degree Celsius, its volume will decrease till 4 degree Celsius, and then from 4 degree it will increase. Okay, so first decreases, then increases. Now question number 9, again anomalous expansion of water question. In anomalous expansion of water, at what temperature the density of water is maximum? So density of water is maximum at 4 degrees Celsius. Okay, this came in 2016. So previously anomalous expansion of water was favorite, then suddenly the laws of Newton's laws of cooling was favorite. So last few years we have seen calorimetry is favorite. Now what knows what will come this year, so be prepared. Okay, this is a very easy simple chapter, and if you want all such chapters whatever we have covered in our lectures, then you have to go to our channel and bookmark our playlist where all the chapters so far we have done is available in one place. You can check at any time you want. Okay, you can study from the lectures that we have done and all the PYQs that we have done. Okay, anytime you can visit here. And if you have not yet subscribed to our channel, you have to subscribe to our channel and join our WhatsApp channel. WhatsApp channel link is given in the description. There we will be sharing all the class notes, all the important updates, also Sunday KPL, everything is happening. And also don't forget to share this video with your friends, whoever is preparing for KCET exam. I hope that will be helping for everyone, and I will be back with a new chapter tomorrow. Till then, bye.